Okay, so we stay with Thomas, but this time Thomas Kluyver from XFEL, and Thomas Kluyver, who has been very, for those of you who don't know this, but he's been incredibly useful also in maintaining H5Pi over the last couple of, or more years probably. I don't know, how many years now, Thomas?
Just a couple of years, I think. I got it 2018, 2019.
Okay, so the floor is yours. Thank you.
Start my screen sharing. Okay, is that working?
Yep, it looks good.
Great, so thank you very much. I am going to talk about virtual data sets and our experiences with those, good and bad, in European XFEL and in the H5Pi project. So my first big contribution to H5Pi was working on the interface to produce virtual data sets in Python. So just in case anyone is not familiar with the term, virtual data sets are a feature introduced in HDF5 1.10, and they point to one or more source data sets, which can also be in separate files. So you can present these separate pieces of data as one bigger data set without having to copy all of the data. So what's actually stored in the virtual data set is just a set of links saying this piece of the virtual data set comes from this data set over here. And for the code reading from this data set, it's transparent, so it just looks like a normal HDF5 data set. You use the same HDF5 APIs to open it and select data from it. But internally, it doesn't have the actual data. And they're fairly flexible. You can use them to kind of like line up different chunks of data that might not be quite aligned naturally. You know, if one bit of data starts sort of a couple of frames later than the other, you can deal with that. You can leave gaps with a fill value in that don't have any data. You can interleave different, one frame from this file, one frame from that file. So first off, I'm going to talk about how we're using virtual data sets at European XFEL. So this is a free electron laser facility just outside Hamburg, which started operations in 2017. So it's still fairly new, and X-ray laser pulses are generated electrons are sent through the red part, and then the orange parts in this diagram convert those to X-ray pulses, and they hit samples and are detected by various kinds of instruments. And all of the data recording is done directly to HDF5. So we don't have an intermediate format to sort of record the data to and then create HDF5 later. It's writing HDF5 directly as we go. And one of the consequences of this, kind of similar to what Wout was saying just before about ESRF, is that the data is written in these chunks. So at European XFEL, they're called sequence files. So the same kind of logical data set. Every minute or so, the exact period is configurable, but every now and then the thing writing the data will close out one file, say I'm done with that, and open a new file with exactly the same structure and start writing into that. So we've got n data sets in n files, which can be anywhere from 1 to sort of hundreds, containing logically adjacent chunks of the same data. And fairly obviously, as similar to what Wout was saying, we can use a virtual data set to stick them back together so they look like one big data set in the file. we don't actually do this as part of writing the files. So unlike ESRF, our files are all written by C++ code. So it's not so easy to add things like virtual datasets. So for us, that's a separate step that comes later, and actually something that we're still working on putting that together. But the other thing is these multi-module detectors. So this is the DSSC detector, and this is one of a few detectors we've got that record from multiple modules. So each one of these kind of strips going across kind of two panels is a module, and there are 16 of those in this detector. And so each one is a 2D array of pixels, and each one records to a separate file. And that's largely to do with the data rate, that getting all of the pixels from all the modules off and into one computer and into one file would be difficult. So they record to separate files. So then we have kind of this 2D logical grid of 16 modules by however many frames the detector has taken. And this is, of course, really a 4D array, because each little block is a 2D image. And we want to piece this together so that if you want to get one complete detector frame, you can just kind of read one row across this grid. And this is a little bit more complicated to produce than the previous example, because some of any module can at any time sort of like miss a chunk of data. And in that case, like there isn't a gap left in the source file. So this piece of data after the gap will be adjacent in the source file to this data before the gap. So we need to kind of introduce a gap in making the virtual data set, and we have code that does that. So turning on to the H5Py part of the talk, the API to assemble virtual data sets was kind of part of my work at European XFEL. Other people had already started proposing interfaces for this, but I came along and kind of finished it up and got it merged. So the core of it is that we're using NumPy style slicing to assemble these source objects into a layout. So here we've just got three sources, so files a.h5, b.h5, c.h5 with corresponding datasets named A, B, and C. And we're going to make a 4x6 dataset of 4-byte integers. And yeah, the first row in that will be from file A, the second row from file B, and so on. And the fourth row is left empty because we don't put anything in it. Yeah, so this is a very concise but flexible interface that lets you put together virtual data sets. This build virtual data set bit specifically is new in H5Py 3.3. The interface from the previous version is very slightly longer, but still works in conceptually the same way. You create a layout object, assemble source objects into it, and then add that into the file when you're done with it. And just for contrast, so that's the complete Python code to make a virtual data set with these three sources. This is part of the C code to do the same thing, and don't try to read that now because I'm going to move on in a moment, but the idea is just to show that it's a lot more concise in Python, and as you can probably see, this isn't even the complete C code. There's other bits that have to come first and afterwards, but this was the core of it. that's roughly equivalent to that Python code. We've also got a shortcut if you've got an existing data set. So as was mentioned earlier, the datasets, virtual data sets, you can create them whether or not the source data sets exist. If they do, then you can create the virtual source from an H5Py dataset object, and that automatically copies all of the necessary information of the file name, the path inside the HDF5 file, and the shape of that. So you don't need to spell that all again. Just a few examples to illustrate the 3D slicing, the multidimensional slicing. So these diagrams are from the HDF5 group document, the RFC for virtual datasets. So we're slicing these 3D arrays in different ways and assembling them into different pieces of the virtual dataset. And this is how you can do it all in Python. So we're slicing in different ways on different dimensions, and also slicing into the layout object to assemble these pieces. And you also have a step argument which you can use to do this interleaving. I can see I'm running a bit low on time, but just briefly, I will go over some of the downsides that the drawbacks that we've run into with virtual data sets. And the biggest one really is that errors reading from the virtual data set appear as empty data. So that includes if it can't find the source file for any reason, if there is a problem with the permissions opening the source file, and a particularly frustrating one for us is that it tries to open the source files with the same mode as the file containing the virtual data set. And of course, our source files are strictly read-only for the people accessing the data, because that's scientific data that's been recorded from an experiment. It's not, you can't change it. But the virtual dataset files are something that we have scripts that people can create on the fly. So often they have read-write permissions to these, and then it tries to open the source files, read-write as well, and fails, and then the data appears empty. This has actually been mitigated a bit because H5Py switched the default file mode to read-only, so it's harder to accidentally open a file read-write, but it can still come up. We made a little command line tool, a sort of partial workaround for this, that you can tell it to check a file containing virtual data sets, and it will identify any virtual data sets, look at what sources they draw on, and check if those sources are accessible, and it tries to give clear information if they're not. So for instance, if I delete one of the source files for this, then it says this source file, no such file or directory. So that's a Python tool you can install with pip, and it's open source, so it's on GitHub. It's tiny, there's hardly anything to it. But this is so this doesn't pick up the thing that I was saying about opening the virtual dataset file read-write, and the source files might be read-only, because that's a problem with how you work with the data, not with the file itself. And overall, it's very much a workaround, not a solution. Other issues, there's kind of a lack of good documentation. There's the main user documentation is still the RFC from 2014, before virtual datasets were actually implemented, and some of the details have changed. And so we've run into questions like someone reported a bug on H5Py saying this thing doesn't work when I try to write through a virtual dataset to source files, and is that even meant to be supported? It's not clear from any documentation. There's some kind of hints that it is, but nothing explicitly saying this is what you need to do, this should work. we've run into a limit with the number of open files that the system can have. So if you've got thousands of source files in a virtual data set, you're trying to read from it, then they will it will hit some system limit on the number of open files, and then you have then it just decides that the rest is empty data because it can't open the files. On our systems, this is like 1024 files by default, and we can raise it to 4096. And kind of uncertainty around performance. So like if you construct the virtual data set in the wrong way, particularly we found if you make a lot of small mappings, which sometimes people try to do, then reads can be very slow, and it's kind of not necessarily clear to users what's going on there. So that is me.
That's it. Okay, thank you. Thank you, Thomas. There was one question which I think Elena also answered was, does VDS work with remote VFDs like S3?
Right, I doubt, and it was never tested, so I would say it does work until it's, but I doubt that it works because of source file name resolution. It is stored in the file, so library has to find source files, and probably it will not.
Okay. I doubt it. Okay. And then I don't know, do you want to say a word about the H5Pi releases? Where are we at today? 3 or no?
Yeah, so 3.3 just came out a couple of weeks ago. Yeah.
I think it's heavily used, so. I don't see any other questions. I doubt, okay. And if anyone, if you have no other comments, you actually rely on this. I mean, the virtual files, VDS, you rely completely on this at XFEL, yeah?
Yeah, so particularly the thing I mentioned with the multimodule detectors. So one of the analysis programs that's very big, XFEL, stereo crystallography, reads HDF files and expects like all of an image to be in one HDF5 file. And so yeah, the ability to assemble different files into one big file without copying sort of terabytes of data around has been really valuable for that.
Thomas, and I can talk with you offline about your comment errors with empty data, what we can do to enhance to, let's talk about it.
And there was a question from Peter about performance. And now I remember in previous meetings, HDF meetings, this performance issue, for instance, at PSI was brought up and so on. I don't know, do you use the performances mainly for the reading? This is the one that you're talking about. You're not talking about writing, no? Or...
So with the multi-module example, again, with those gaps that you have to account for, like kind of the easiest way to do it is to map sort of each square in that grid I showed as a separate mapping. And then you end up with thousands and thousands of mappings and the performance goes very badly. So like just empirically, what we've found is that if we take care to make like as few large mappings as possible, then the performance is quite acceptable. I haven't actually compared it to kind of reading all of the same data without a virtual data set.
Okay.
It works okay.
I don't know if this could be part of the discussion, maybe this off at the end. But thank you.